Emission Engineering presents EVEN, the next level of furnace operation. Hello, and welcome to Emission Engineering. We will introduce you to a new and exciting tool, a tool that makes it very easy to optimize fired heaters in oil refineries and petrochemical plants with respect to efficiency and emissions. But before we focus on that, we would like to give you some background information and to explain why we believe that the majority of today's fired heaters do not operate optimally. Have a look at the sketch on this slide. You can see a furnace with 6 forced draft burners. The amount of air that is conveyed to each burner is normally not measured. Let's assume that the burners receive the same amount of fuel and therefore have the same heat release, but the air distributes unevenly. That air distribution can be poor is something that we've seen many times and is therefore more likely than not. Furnace or burner providers sometimes use physical or computational fluid dynamics modeling in order to improve air distribution, and if done correctly, this is certainly better than doing nothing. But there are cases in which modeling was done and air ducts were adapted in size, and an adequate cross-section air distribution was found, if at all, only for a certain operating point. For a different operating range, air distribution remained poor. If we could measure separately the oxygen concentration of each burner, for example, right at the end of each burner flame, we could detect uneven air distribution by different oxygen levels, as shown in the oxygen profile in this slide. In this figure, burner 1 and 5 are receiving more air, while burner 4 is starving on air and already producing higher carbon monoxide emissions. If there is just one oxygen measurement device located somewhere above the burners, typically at the bridge wall, we cannot be sure from which burner a certain oxygen or carbon monoxide emission is coming from, because the mixing quality of the flue gas of the different burners is unknown. So we might be measuring the oxygen content of burner 2 or 3 and 4, or 2, 3, and 4. Nobody knows for sure. Something similar would happen if we measured nitrogen oxide emissions independently. The main nitrogen oxide formation mechanism in fuel gases without fuel-bound nitrogen is the so-called thermal NOx mechanism. This means the higher the temperature peak inside a flame, the more nitrogen oxide is produced. Besides temperature, the partial pressure of oxygen also influences nitrogen oxide formation. Most often, the more excess air a burner operates at, the more nitrogen oxide it produces, at least in the range between 1 and 5 or 6 volume% of oxygen. Above this oxygen content, the flame cooling effects may reduce nitrogen oxide again. Why are we telling you all this? Where is the relevance for your furnaces? As a matter of fact, refinery personnel very often firmly trust their existing oxygen analyzer, even if it may not be reflecting reality. But sitting back and thinking everything is fine when the DCS is measuring 2% volume of oxygen can even be dangerous. In our previous example, did you detect burner 4 was starving on air? The starving may cause some stability problems of the flame, with some likelihood of main flame self-extinction. When no main flame detectors are in place, the situation can quickly get out of control, even if pilot burners are turned on a continuous basis. What do we do nowadays when oxygen is either too high, or fluctuates, or carbon monoxide emissions are popping up and disappearing? Well, normally, field operators try to readjust the burner air dampers according to either their physical flame observation or their experience of what they need to change in each burner in order to achieve the desired effect. In the example above, let's say that the oxygen analyzer captures a mixture of flue gas from burners 3 and 4. This means that the burner air dampers of burners 3 and 4 are opened up, and the effect can be seen on the oxygen analyzer. But the conditions of burners 1, 2, 5, and 6 would remain unchanged because the total airflow rate is kept constant by a fuel-to-air ratio control loop in the DCS. Thus, the furnace is treated so that the oxygen analyzer conditions are satisfied, but this isn't necessarily the best for all burners. Coming back to the way oxygen is measured, some refineries think they are able to resolve all problems with a different type of oxygen measurement device. Those mainly used are zirconium dioxide-based oxygen analyzers because they are more economical than those we will mention shortly. They provide single-point measurements, however, and the point that is measured may not be representative of the operation of all the burners. Extractive oxygen measurement devices are more accurate, but they have slower response times, and in addition, they still provide only single-point measurements. More advanced, although more expensive than the zirconium dioxide-based analyzers, are laser-based analyzers. They measure the average oxygen content along the running length of a laser beam. They offer a so-called line measurement, which is obviously more representative than a single-point measurement, but still has some defects. Going back to our example, do you think the laser would detect the lack of air in burner 3? Please note that we have not yet discussed Tramp air ingress into the heater. As fired heaters are normally operated at negative pressure, Tramp air can never be fully avoided. The more Tramp air that is sucked inside a furnace, the more likely it is that the oxygen value, regardless of the method used to measure it, will not reflect reality. In a worst-case scenario, Tramp air falsifies the oxygen content of the flue gas to such an extent that the burners start to lack air, even when the measured oxygen content still seems to be within the desired range. This can cause serious safety problems. The most important norm concerning fired heaters, at least in Europe, is the DIN EN 7462, Thermal Processing Equipment Part 2, Safety Requirements for Combustion and Fuel Handling Systems. Chapter 5.2.3.3 of this norm indicates that the airflow rate must be put in a ratio with the fuel flow rate in a way that it can be always safely ignited and delivers a stable flame and combustion across the entire operating range of each individual burner. Take a look at the oxygen concentration profiles on this slide. How do you think this requirement can be fulfilled in a multiple burner system with only one oxygen analyzer that is not necessarily measuring on a representative basis, nor taking Tramp air ingress into consideration? There are other norms like API 535 or API 556 that say similar things, but it's curious that none of them tells exactly how the proper fuel-to-air ratio on every burner can be achieved. This is why we came up with a very practical way to approach the problem. The idea is, if you can make, in a way that we'll explain shortly, the fuel-to-air ratio the same on each burner, then it doesn't matter where exactly your oxygen analyzer is located, because all the burners will produce the same amount of excess oxygen, in our example, 2.5 volume%. Probably everybody will agree with this idea. Even furnace producers say it in their operating manuals. Operate all burners in the same way, meaning with the same fuel-to-air ratios. But unfortunately, end users are often left on their own as soon as the guarantee of their furnace runs out. We will explain now how to achieve uniform fuel-to-air ratios on all burners. The optimizing tool we will use is called EVEN and was developed by us at Emission Engineering. The system is currently under patent pending status. Before we start, there are two important prerequisites that must be met so that EVEN can work properly. All burners connected to an EVEN system must have the same airside pressure drop at the same flow rate constantly over time. We will explain on the next slide what this means. Likewise, the heat release must be either the same on all burners or at least known in relative values for each burner or group of burners. In principle, EVEN can be applied to furnaces with natural or forced draft burners and is not limited to the furnaces of oil refineries. It can also be used in, for example, slab pusher furnaces in steel mills, non-regenerative burners of glass or aluminum melting furnaces, and many others, although not in every type of system. In order to understand what we will be measuring, let's explain first the phrase airside pressure drop of a burner. What is the airside pressure drop? Take a look at the graphic. On the left, you will see the side view of a burner with its air inlet, air damper, wind box, tile, and throat section. The throat section of a burner is where the main pressure drop of combustion air should occur. We say should because unfortunately it doesn't always occur there. If the main pressure drop happens in the right place, meaning the smallest cross-section where the air must pass through, the air velocity will be highest, and therefore the mixing with the fuel will be most efficient. To make clear what the throat of a burner is, we have colored it in red on the picture on the right of the slide. Now let's imagine you could ride on the back of a flow filament of air through the burner, and you could measure the pressure drop on the different sections of the burner. You would then see that the throat section makes for approximately 75% of the total pressure drop. This is even a requirement according to the API 535 norm dated January of 2006. In the latest draft of the APA 535, dated May of 2014, this criterion was removed, unfortunately in our opinion. Rumor has it that the latest ultra-low NOx burner technology doesn't like high airside pressure drops, and that might be true. But the disadvantage of lower airside pressure drops is that the air duct header pressure is lower, and consequently, the air distribution on forced draft burner systems is worse. What do we gain by measuring this part of the total air pressure drop across the burner's throat? Well, it's commonly known that, according to Bernoulli's law, pressure drops follow a quadratic correlation with the flow rate. By using the burner throat literally as a flow orifice, we can get information from the pressure drop about the airflow going through the burner. The higher the airflow through one burner, the higher the pressure drop will be. Assuming that the heat release is the same on all burners, we can conclude that all burners need the same amount of air, and this translates into the same air pressure drop through all the burner throats. Okay, now that we are acquainted with the fluid dynamics background of EVEN, we will explain how furnace optimization should be carried out. In step 1, we need to check if the heat release of all the burners is the same. If only one and the same fuel gas is used, which is the most frequent case, then fuel will distribute evenly according to high fuel gas pressures. We assume that the fuel gas tips are clean and have the same drilling ports. Of course, it will all become trickier if there is more than one fuel operating at the same time, but more about this case at a later stage. In step 2, the air must be adjusted evenly. Therefore, the airside pressure drop across all burner throats needs to be measured and displayed, ideally in one central place close to the furnace. If the pressure drop differs from one burner to another, the air dampers will need to be adjusted until uniform air distribution is achieved. Step 2 is actually the only new step. Step 1 and 3 remain as they have always been. In Step 3, the total combustion airflow rate will be reduced until the desired excess air level is achieved. This slide shows exactly how the optimization and reduction of excess air works when it is correctly performed. In yellow, you can see the heat releases of every burner. All the burners operate at 2 megawatts. The operator does not receive this information directly, neither from the DCS nor from the field, but it can be derived by checking the fuel gas pressure at each burner inlet and deriving the heat release from that pressure using the burner capacity curves for a certain fuel composition provided by the burner vendor. In practice, Step 1 would therefore consist of checking the fuel gas pressure upstream of the burners. If the pressure is the same on all the burners, then the heat release will also be the same. If no pressure gauges are available, it is a reasonable assumption that the fuel gas will distribute evenly among the burners as long as they operate at a decent fuel gas pressure, for example with more than one bar gauge, and the gas tips are in adequate conditions. Step 1 is herewith finished. In Situation 1, you can see now the burner air damper settings in green. Normally, before any tuning is done, they are fully open in forced draft burners. In red, you can see the readings of the airside pressure drops across the burner throats. You may note that the pressure drop on burner 4 is the highest, with 158 millimeters of water column, while it is lowest on burner 2. The conclusion is that burner 4 receives more air than the others. In order to compensate for a higher flow rate, a field operator will need to adjust the air damper of that burner. Step 2 therefore consists of changing the air damper settings of the burners. In Situation 2, you can see how the air damper of burner 4 is partially closed, from being 100% open to only 80% open. As a consequence, the pressure drop of burner 4 decreases, while those of burners 1, 2, and 3 increase. Why increase? Because, as was said before, the DCS will keep the total flow to all burners constant, either through the total fuel to total air ratio or through the oxygen measured, although using oxygen measurements implies that all the flue gases from all the burners mix perfectly, which is something that normally cannot be assumed. Step 2 finishes when all pressure drops are the same. In our example, 150 millimeters of water column. You can see that the air dampers may be different on all the burners. Once this is done, these settings may be suitable for a wide operating range of the furnace, although most likely, if the load is low or very low, they will need to be adjusted again. Once uniform air distribution to all the burners is achieved, and only then, the total excess air can be lowered. It's clear that, without proper air distribution, any excess air adjustment with the help of the oxygen analyzer will be pure luck or fake. In Step 3, the total combustion airflow is reduced, either by changing the set point for the oxygen target in the DCS or by adjusting the excess air factor in the fuel-to-air ratio control loop. In Situation 4, you can see the results once the volume percent of oxygen is reduced to 2 or 1. In both cases, the pressure drop variance remains the same, only the absolute value goes down as the airflow goes down. You can see that a reduction from 3 to 2, 1, or only 0.5 volume percent of oxygen doesn't translate into a big difference in the absolute pressure drop. In the example, it drops from 150 to 146, 142, or 141 millimeters of water column respectively. This proves that optimization from 3 to lower oxygen levels requires proper fuel-to-air ratios in all the burners. Otherwise, carbon monoxide emissions start breaking through in one or more burners, even if the overall oxygen content still looks okay. It also requires measurements that are accurate enough to let the operator see even small differences in the pressure drop, especially when natural draft burners are used, because they have a considerably lower delta P than forced draft burners. Borden-type pressure gauges are too delicate and not suitable in our opinion. Do you think this method is too time-consuming and complicated to understand? We assure you it's not. The measuring systems that we have in continuous operation are widely accepted, and in relation to the time effort, it is actually the opposite. In earlier days, it was very time-consuming to search for one or more burners operating too close to stoichiometric conditions and therefore producing carbon monoxide. Now you can see that one glance is enough to perceive which burner has received more or less air, and with just a few quick damper setting changes, an even distribution is achieved. This allows field operators to focus on other critical equipment. In addition, the way potential fuel savings are looked at will change. You may have measured 3 volume percent of oxygen in your flue gas, whereas in reality you may have had 5 or more volume percent. And this may lead you to believe that everything that could be done to reduce excess oxygen has been done. But fuel savings could not be achieved because the oxygen measured was not representative. Now, having more reliable oxygen data helps fuel savings become a reality. Even can also be used if burners are not operating on the same heat release and also for NOx reduction. More information on that subject, as well as real implemented case studies, including ethylene cracking furnaces, can be obtained at Emission Engineering. Contact us. We are often asked about the savings derived from excess air reduction. This is why on this slide we have tried to calculate some savings in euros per reduction of excess air. Of course, potential savings depend on the size of the refinery concerning the heat release to all furnaces and the real average oxygen contents in the flue gas. Again, as measurements of oxygen levels are very often non-representative, savings may appear smaller than they actually are. In our experience, most fired heaters have the potential for further excess air reduction, here highlighted in green. Even a small reduction can quickly lead to savings in the 7-digit range, as the total heat release is pretty high in refineries. Considering that fuel costs are quite significant in the process of processing crude oil and the resulting products, the return on investment in this area is very quick because our tool can be implemented without additional hardware like heat exchangers, etc. Let's summarize. With the Even Optimizing tool, it is possible to adjust fuel-to-air ratios in every burner with little effort. The claim of norm DIN EN 746-2 for fuel-to-air ratios within certain thresholds can be achieved with Even, the application of which leads to better combustion conditions, translating into safer operation. Fuel savings by excess air reduction are achievable in reality, not only on paper. Oxygen measurements become more reliable and representative through the usage of Even. Adjusting fuel-to-air ratios so that they are similar in all the burners leads to lower peak temperatures in the flames, which translates into a more uniform heat transfer to the product tubes, fewer so-called hot spots, and therefore less coke formation inside the product tubes. Coke formation decrease alone can be a decisive economic factor. The best application of Even in relation to critical coke formation is on ethylene cracking furnaces. Even's main target in ethylene furnaces is to prolong cycle times between decoking phases by avoiding hotspots. Finally, a few last words about the hardware used by our optimizing tool Even. We have developed different versions. Version 1 is a totally non-electrical pressure drop measurement device. It can be applied in non-classified areas as well as in explosion areas, for example in Zone 1 Gas Group 2C. Our main target during the development of this version was to keep the cost of the hardware down without losing any process information, which is the air distribution to all burners. One can see how, in heaters without any air pressure drop information, the process information boosts up from 0 to practically 100%. See the red line on the graph. In version 1, burner air dampers are moved by the field operators themselves, just as usual in most furnaces today. As mentioned earlier, the time effort devoted to burner adjustment by the operators is reduced, which means more time can be spent on other equipment. Meanwhile, safety is increased. The time required to install the equipment is very short. Besides the delivery time, which is approximately 3 months, even can be instantly applied to a running heater without the need for a furnace shutdown. Version 2 works just like version 1, but has electrical transmitters displaying the airside pressure drop values on a small touchscreen. The process information remains the same. There is just a bit more information available to the operators, for example, the number of the burner whose air damper it is suggested to move first. This version is more costly, which is why we normally use it for demonstration purposes only. This means we have portable equipment on hand with which we travel to site and measure the air distribution with practically no investment on the part of our clients. You can see the portable version in the photo to the right. 2 more versions are possible, but not necessarily always meaningful. Version 3, instead of locally indicating the air distribution, has it displayed on the DCS. This version requires a lot of cabling from the field to the DCS, as well as power supplies for the pressure transmitters. Furthermore, the DCS software needs to be programmed and the process information is gathered in the control room when it is the field operator who actually needs it the most. Having close access to the furnace and visual observation of the flames is still being required in case of inspection or troubleshooting. Finally, version 4 does everything version 3 does, but it automatically controls each burner air damper based on pressure drop. It requires control dampers, actuators, positioners, etc. on each burner and each air damper. The cost of this version is significantly higher than the cost of version 3, and even more so compared to version 1 or 2. Moreover, extensive HAZOP meetings may be required to implement the correct safety procedures for this version. Our recommendation is to stay with version 1. It is simple, robust, relatively inexpensive, and easily and quickly implemented. It needs practically no maintenance, and it doesn't eat up your time or your resources for planning, controls, HAZOP, etc. We have been commercializing EVEN since November 2015. There are several units in permanent service in furnaces of oil refineries. A few more units are at client sites as rental equipment. The return on investment is so great that EVEN pays for itself in less than 2 to 4 months. EVEN is therefore an incredible tool that improves your fired heater operation significantly. If you're interested in getting first-hand information from one of our customers, we will be glad to put you in contact with them. Feel free to contact us also if you have questions or would like to receive a commercial offer for your specific furnace. If you're interested in learning more about EVEN, the possibility of using it when heat release is uneven, for NOx reductions of up to 25%, or to extend the decoking cycles of ethylene cracking furnaces, please send us an email with your contact details and we will be glad to send you more information. Our email address is ee@emission-engineering.com. Thank you for your attention. Emission Engineering. We engineer your emissions.